What is Hugging Face? Hugging Face is an open source first artificial intelligence platform that provides the infrastructure, tools, and collaborative ecosystem required to build, share, fine-tune, evaluate, and deploy machine learning models. It places particular emphasis on transformer-based architectures, generative AI, and reproducible research. In practice, Hugging Face functions as the central distribution and collaboration hub for modern machine learning, often described as the GitHub of machine learning. Founding and evolution, it was founded in 2016. The founders are Clement DeLong, Julian Chomond, and Thomas Wolfe. Hugging Face originated as a conversational AI startup. Its strategic pivot occurred with the open source release of the Transformers library in 2018 and 2017, which rapidly became the standard interface for transformer-based models: BERT, Roberta, Albert, Electra, and so many models like GPT and Qwen, DeepSeek, Llama in both academia and industry. This release catalyzed Hugging Face transformation into the leading open platform for AI research, development, and deployment. Core users. You can see here the most core users here is a model hub, so host and version, pre-trained and fine-tuned models, datasets hub, libraries and tooling. Hugging Face offers us multiple libraries like Transformers, Diffusers, Accelerate, and so much libraries like Gradio, Spaces and Gradio, Inference and Deployment, Research and Education, reproduce papers, benchmark models, and teach modern AI workflows. The importance and impact of Hugging Face: democratization of AI lowers barriers to entry through free, open, and standardized tooling. Open science leadership encourages transparency via model cards, dataset cards, and reproducible benchmarks. Industry adoption, trusted by startups and enterprises for rapid prototyping and production deployment. Research acceleration, ecosystem standardization establishes common APIs and workflows across frameworks and modalities. Community scale hosts millions and millions of models and datasets maintained by a global contributor base. And here we have the images of the authors of the Hugging Face platform. Hugging Face philosophy and ecosystem vision. Why Hugging Face exists? Hugging Face exists to make state-of-the-art artificial intelligence accessible, reusable, and collaborative. Its core mission is to remove friction between AI research and real-world application by providing a shared platform where models, datasets, and applications can be openly published, discovered, improved, and deployed. Rather than treating AI artifacts as closed products, Hugging Face treats them as living research objects that evolve through collective contribution. Here you can see democratization of AI and open science, open source libraries. So their libraries are all open sourced that lower entry barriers for learners, researchers, public model and dataset sharing that enables reproducibility and transparent comparison results. So there are so many datasets available on Hugging Face, as well as models for free, model cards and dataset cards that document training data, intended use, limitations and ethical considerations, open access to research artifacts that accelerates innovation across regions, institutions, and economic contexts. Community-driven research versus closed AI platform. Hugging Face represents a community-first paradigm for AI development. Researchers publish pre-trained models together with code and weights. So there are so many pre-trained models like text-to-image models, image to text, video to video, text to video, and also we have image to video. Practitioners fine-tune, evaluate, and adapt existing models to new domains. Improvements propagate rapidly across the ecosystem through reuse and remixing. Hugging Face as GitHub for machine learning. Hugging Face fulfills the same role for machine learning that GitHub fulfills for software development. repositories for models, datasets, and machine learning applications, versioning, updates, and collaborative workflows, discoverability through search, tags, leaderboards, and benchmarks, standardized documentation, licensing, and attribution. This analogy reflects Hugging Face's position as the default distribution, collaboration, and archival layer for modern AI artifacts. So here you can see the relationship with academia, startups, and enterprises. Hugging Face operates as a neutral connective layer across the AI ecosystem. Academia enables reproducibility of papers, and there are so many papers hosted on Hugging Face, open benchmarks, and rapid dissemination of research outputs. Startups supports rapid prototyping, fine-tuning, and deployment with minimal infrastructure overhead. Enterprises provides secure and scalable solutions for private models, managed inference endpoints, and production workflows. And then we have the Hugging Face platform architecture. So how the Hugging Face Hub works internally. At its core, the Hugging Face Hub is a Git-based content address platform designed to host and serve three first-class AI artifacts: models, datasets, and spaces. And if you visit the homepage of the Hugging Face platform, you will see these three tabs at the top navigation bar: models, pre-trained weights, configurations, tokenizers, and inference metadata. Datasets, structured data with schemas, splits, streaming support. Spaces, executable applications, Gradio or Streamlit built on top of models. Each artifact is stored as a repository. So keep in mind, each artifact, whether it was a model or dataset, it will be stored as a repository with standardized file layouts and metadata, enabling discoverability, reproducibility, and seamless integration with the Hugging Face libraries. And then you can see here we have the versioning aspect, commits, branches, and model cards. The hub adopts familiar Git semantics for machine learning assets. Commits and branches track changes to model weights, configurations, and supporting code. Tags and revisions pin exact versions of models or datasets to ensure reproducibility. Model cards and dataset cards, structured documentation describing intended use, limitations, training data, and evaluation results, biases, licensing, and ethical considerations. This design ensures that models are not merely downloadable files, but auditable, well-documented scientific and engineering artifacts. Model lifecycle upload. So first we start by uploading that model, then we have a version, then we have inference layout, and then we have deployment. Hugging Face supports the full end-to-end lifecycle of machine learning models. First, we start by upload. So push models or datasets via CLI. So it's called CLI, command line interface, Git, or API. Versioning, iterate through commits and branches as models evolve. Inference, run models through widgets, pipelines, interfaces, or hosted inference APIs. Deployment, serve models using spaces, managed inference endpoints, or self-hosted runtimes. This unified workflow removes the traditional gap between research, experimentation, and production deployment. And you can see here we have some public, private, and gated repositories. So keep in mind, this is a really important note. We have public repositories, private repositories or private models, and also we have gated models or gated datasets. Hugging Face supports multiple access control. We have some control access modes to balance openness with responsibility. Public repositories, fully open and accessible to everyone. Private repositories, restricted access for individuals and or organizations. Gated repositories, publicly visible metadata, but access to files requires approval or license acceptance. So there are some public repositories which are fully open, fully accessible, and to everyone. We have private repositories. These repositories are restricted to some individual people or some organizations. gated repositories, publicly visible metadata, but you need to act, if you need to access it, you have to provide some approval or license acceptance. This flexibility enables ethical data sharing, controlled model release, and enterprise-grade workflows. Then here we have the authentication, tokens, permissions, and organizations. Security and collaboration are managed through a robust access control system. User tokens authenticate API, CLI, and programmatic access. Fine-grained permissions assign read, write, or admin roles. Organizations enable shared ownership of models, datasets, and spaces. Team collaboration, role-based access for scalable multi-user workflows. These mechanisms allow Hugging Face to function as a secure collaboration platform from individual researchers to large enterprises. Hugging Face Hub. The Hugging Face Hub is a central registry and distribution layer of the ecosystem. It hosts models, datasets, and applications as versioned, documented, and reproducible repositories that integrate directly with the Hugging Face libraries and external machine learning workflows. Model Hub. Model repository structure. Each model is sold as a Git-backed repository containing standardized components. Model weights. So you need to upload a file that contains model weights, configuration files, tokenizers for or feature extractors. So if you are uploading an LLM, large language model, you need a tokenizer or a type of tokenizer, metadata for inference and evaluation. This structure allows models to be loaded programmatically with a single identifier and reproduced reliable across environments. Model cards, purpose, limitations, ethical notes. Model cards are a core design principle of the Hub. They provide structured documentation covering intended use cases and target domains, training data sources and assumptions, known limitations and failure modes, bias, fairness and ethical considerations, licensing and citation information. Model cards ensure transparency, accountability, and responsible reuse. So first we have the model weights. You can see here typical model repositories include weights in a .bin, .pt, so short for PyTorch, or .safetensors. This is also a package inside Python called safetensors. You will see it a lot common in Hugging Face. Configurations, here we have config.json defining architecture and hyperparameters. So the configuration file, which has the extension .json, JavaScript object notation, defines architecture and the hyperparameters, tokenizes vocabulary files and tokenization rules, safetensors secure memory efficient weight format, preventing arbitrary code execution. These components enable safe and efficient loading across frameworks and deployment targets. Inference widgets. The Hub provides also built-in inference widgets that allow users to run models directly in the browser, test inputs and outputs interactively, validate model behavior without writing code. So the inference widgets, like for example Gradio, it provides the ability to run models directly in the browser without the need to download any model, test inputs and outputs interactively on the web, validate model behavior without writing code. Widgets act as instant demos and lightweight validation tools. Supported frameworks. So the supported frameworks and libraries are PyTorch, TensorFlow, JAX, and Flax. The Model Hub natively supports PyTorch, TensorFlow, JAX, Flax. This framework agnostic design allows researchers and engineers to work in their preferred ecosystem. So whether you are excellent at PyTorch or at TensorFlow, no worries, you can upload your PyTorch model or your TensorFlow model onto Hugging Face Hub. This framework agnostic design allows researchers and engineers to work in their preferred ecosystem. Then let's dive into Dataset Hub. Dataset repository structure. Datasets are stored as repositories containing raw or process data files, loading scripts or dataset builders, metadata, and documentation. They integrate seamlessly with the datasets library. So there's a library called datasets, and then we have the datasets card. You can see dataset card document, data sources and collection methodology, dataset structure and features, licensing and usage constraints, biases, ethical concerns, and limitations. Then let's dive into splits, features, and schemas. Datasets are defined with standard splits, training dataset, validation dataset, test dataset, explicit feature types and schemas, and also automatic validation and consistency checks. And also we have streaming datasets. Hugging Face supports dataset streaming, allowing loading data without full local downloads. So you are also able to load a data without the full local downloads, training on massive datasets efficiently, and reduce storage and memory requirements. And also Hugging Face supports large-scale dataset hosting, terabyte scale datasets, high throughput access, global availability. This makes it suitable for both research benchmarks and industrial scale corpora. Then also we have the Spaces Hub. What Spaces are and why they matter. Spaces are hosted machine learning applications that turn models into interactive demos or products. They provide a fast path from model to user-facing experience. So you are moving from a model in a Google Colab into a model that faces the user, a user-facing experience. Gradio versus Streamlit Spaces. We have two types of spaces. We have Gradio and we have Streamlit. Gradio spaces ideal for ML-centric, component-based interfaces and demos. Streamlit spaces better suited for data, dashboards, and analytical applications. Both options enable rapid deployment with minimal infrastructure setup. Hardware options. We have GPU, we have CPU, Central Processing Unit, GPU, Graphical Processing Unit, 0 GPU. Spaces can run on CPU, lightweight demos and inference. So if you have a lightweight model, for example, a model that is used to classify rows, a structured data, or for example, a model that is using a regression algorithm, you can run it on a CPU. And also we have GPU, heavy models and real-time generation, where you have computer vision models, NLP models, LLM models, reinforcement learning models. They all are heavy models that need real-time generation. 0 GPU, shared on-demand GPU resources for cost efficiency. So the hub summary, the Hugging Face Hub unifies models, datasets, and applications under a single versioned and documented platform, making it the global backbone for sharing, testing, and deploying modern AI systems. Transformers Library. One of the most important libraries inside Hugging Face is the Transformers Library. Architecture of the Transformers Library. The Transformers Library is the core execution engine of the Hugging Face ecosystem. It provides a unified abstraction layer over thousands of transformer-based architectures, while remaining frame agnostic. Internally, it standardizes model configuration and weights, tokenization and feature extraction, task-specific heads on top of shared backbones, consistent APIs for training, evaluation, and inference. And keep in mind, Transformers Library is framework agnostic. This design allows a single model to be reused across multiple tasks and domains with minimal modification. Then we have some classes like the Auto Model and Auto Tokenizer philosophy. At the heart of Transformers is the Auto abstraction. Auto Tokenizer, Auto Model. Auto Model selects the correct model class based on the configuration. Auto Tokenizer loads the matching tokenizer automatically. This removes architecture-specific by boilerplate and ensures correct pairing between models and pre-processing logic, enabling rapid experimentation with minimal code changes. So we have pairing between models via Auto Model and pre-processing via Auto Tokenizer, where you pre-process some text data. Pipelines abstraction. Pipelines provide a high-level, task-oriented interface that bundles pre-processing, model inference, post-processing. So if you use a pipeline by going from transformers import pipeline, this pipeline function provides a high-level, task-oriented interface that bundles pre-processing. You don't need to execute any pre-processing code anymore, model inference, and post-processing. They allow users to perform complex tasks such as translation or summarization in a single line of code, making transformers accessible to beginners while remaining powerful for rapid prototyping. Training versus inference APIs. Transformers clearly separates concerns between inference APIs, training APIs. Inference APIs optimize for speed, simplicity, and deployment. Training APIs designed for flexibility, customization, and large-scale fine-tuning. This separation ensures that production inference remains lightweight while training workflows remain expressive and extensible. Trainer API versus custom training loops. The library supports two complementary training paradigms. Trainer API, a high-level training loop handling logging the values, for example, loss value or the accuracy value. It logs it into some form of list, evaluation, checkpointing, and distributed training. Custom training loops, full control using native PyTorch, TensorFlow, or JAX for research and advanced optimization. This dual approach balances ease of use with research level flexibility. Tokenizers integration. Transformers integrates tightly with the Tokenizers library. Fast, Rust-backed tokenization, and you know Rust is the most fastest language in the world. Support for byte per encoding, word piece, unigram, and sentence piece. Consistent pre-processing across training and inference. Tokenization is treated as a first-class, reproducible component of every model. Supported tasks. The Transformers library supports a wide range of AI tasks, including text generation, autoregressive and instruction following models, classification, for example, sentiment analysis, topic classification, intent detection, question answering, QA, extractive and generative AI, QA, named entity recognition, NER, structured information extraction, translation, neural machine translation across languages, summarization, abstractive and extractive summarization, multimodal vision, language, audio, text, and video-based models. And here we have the paper of BERT, bidirectional encoder representations from Transformer, which uses the encoder-only transformer architecture by Jacob Devlin and et al. BERT fundamentally changed language modeling by proving that deep bidirectional pre-training yields richer contextual representations, setting a new standard for transfer learning and becoming the backbone of modern NLP systems. And here, feel free to read this paper in your own time. You can see here we have view inline, and it will shows us a model or opens up a model containing the BERT paper. And you can see here we have the BERT paper. And this is the architecture of BERT. Pre-training followed by fine-tuning. And also, here we have an implementation of BERT. If you go to Colab, it will direct you to our Colab environment that we will explain the Transformers library using it. So you can see here, this is the Colab environment for Transformers library, and we will explain this code step by step, line by line, code by code in an upcoming section. And also we have here the Hugging Face that directs us to the Hugging Face model card of the BERT model. You can see BERT base model uncased, and he has used this model. It says Transformers library. If you open this, it will show you a model that contains two distinct ways to load in the BERT model. You can see Google BERT/BERT base uncased. Now let's go to the next idea here, and also we have the GitHub that directs you to the GitHub repository of this course, Hugging Face course. Here we have the Transformers library tutorial that we will explain it in this course, where we performed here machine translation, named entity recognition, sentiment analysis, and also tokenization and generation via a GPT-2 model, and also RAG with question answering model. Now let's dive into model families and architectures. This section categorizes the major model families and architectural paradigms supported across the Hugging Face ecosystem. The goal is to provide a clear mental map of architectures explaining why different models exist and which problems they are designed to solve. Encoder-only models, BERT-like. Encoder-only architectures process the entire input sequence bidirectionally, producing rich contextual representations. Optimized for understanding tasks, so they are optimized for natural language understanding, NLU, common uses, classification, NER, named entity recognition, sentence embeddings, extractive question answering. Examples: BERT, Roberta, Distelbert, Albert, DBERTA. These models excel at representation learning rather than text generation. Then we have decoder-only models, GPT-like. Decoder-only architectures generate text autoregressively, predicting the next token given the previous context. Optimized for generation and reasoning. Common uses: text generation, chat, code completion. Examples: GPT-style models, Llama, Mistral, Falcon, Quinn. They form the backbone of modern large language models, LLMs. So here we have encoder only, like BERT, Roberta, Distelbert, Albert, DBERTA. They are optimized for understanding tasks. They understand the language very well. Common uses: classification, named entity recognition, sentence embeddings, extractive QA, question answering. But here we have decoder only, which excel at text generation, chatting, code completion. Optimized for generation and reasoning. The core idea: autoregressively, they generate via an autoregressive mechanism and algorithm. And also we have encoder-decoder models like T5 and BART. Encoder-decoder architectures combine bidirectional understanding with autoregressive generation. And here, keep in mind, here we say BART, not BERT. Input is encoded into a latent representation. Output is generated conditionally from the encoded input. Common uses: translation, summarization, text-to-text tasks. Here you can see the main use cases are not text generation, but rather translation, summarization, text-to-text input tasks. And if you know the paper, attention is all you need. In that paper, they proposed a transformer architecture which was consisting of an encoder and decoder, the same as this, and they used it for translation task. So the encoder-decoder architecture is best suited for translation and summarization. Examples: T5, BART, and Marian. These models unify many NLP tasks under a single sequence-to-sequence framework. So the sec-to-sec, where we receive a sequence, we encode it into very rich representation vectors. Then we guide the decoder produces another sequence. And also we have vision transformers, VIT and SWIN. Vision transformers adapt the transformer architecture to image data. Images are split into patches and embedded as sequences. Self-attention models, global visual context. Examples: VIT, vision transformers, SWIN transformer, and DIT. They replace convolution inductive biases with attention-based perception. And also we have multimodal models like CLIP, Flamingo-like. Multimodal architectures align or jointly process multiple data modalities, text, image alignment and grounding, cross-modal retrieval, and multimodal generation. Examples: CLIP, Flamingo-style models. These models enable vision, language understanding, and generation. Also, we have speech models, code models, diffusion models. Like diffusion models generate data by iteratively denoising latent representations. High fidelity image video generation, controlled generation via conditioning signals. Examples: Stable diffusion and other latent diffusion variants. These models dominate modern generative vision workflows. Let's dive into the Diffusers library. Diffusers library, generative vision, and multimodal. The Diffusers library is Hugging Face's core framework for diffusion-based generative modeling. It translates diffusion theory into a modular, production-ready system for high-quality image, vision, audio, and multimodal generation. Diffusion theory, DDPM, so denoising diffusion probabilistic model, DDIM, SDA's stochastic differential equations. Diffuses is grounded in diffusion probabilistic modeling, where generation is framed as a gradual denoising process. DDPM, denoising diffusion probabilistic models, learn to reverse a fixed noise schedule through iterative denoising. DDIM, denoising diffusion implicit models, deterministic or semi-deterministic sampling for much faster inference. Score-based models, SDAs, continuous time formulations, enabling flexible noise schedules and stronger theoretical grounding. And also here we have the diffuses pipeline abstraction. Diffuses introduces a modular pipeline abstraction that cleanly separates concerns, model components, unit, VAE, variational autoencoder, text encoder, noise schedulers, conditioning inputs, sampling logic. This design allows rapid experimentation by swapping components without rewriting core generation code. Stable diffusion ecosystem. Diffuses serves as the reference implementation for the stable diffusion ecosystem. Latent diffusion for computational efficiency, text to image, image to image, in painting and out painting, seamless integration with community checkpoints and extensions. Also, we have ControlNet, LoRa, and Dreambooth. Diffuses supports advanced conditioning and fine-tuning techniques. ControlNet, LoRa, Dreambooth. LoRa is a parameter-efficient fine-tuning with minimal memory and compute overhead. ControlNet, structural control via edges, depth maps, pose estimation, or segmentation. Dreambooth, subject-driven personalization using small, curated datasets. And here you can see image, video, and audio diffusion. The diffusion model is best suited for image generation, video generation, and in some cases, audio generation. Diffuses extends diffusion modeling beyond images. We have video generation with temporal coherence and motion modeling, audio generation with waveform or spectrogram-based diffusion, multimodal generation with joint text, image, and audio conditioning. And also we have here performance optimizations, memory efficient attention, mixed precision inference, model sharding, and CPU GPU offloading, optimized schedulers and sampling strategies. And also you can see here we have a paper of pre-training of deep, or the paper that is of deep unsupervised pre-training using non-equilibrium thermodynamics, and feel free to read that paper in your own time if you like. Here we can open this paper and we'll see deep unsupervised learning using non-equilibrium thermodynamics by Jasha Soldikstein and et al. And you can also go to the Hugging Face. It will direct you to the Stability AI Stable Diffusion XL base 1-0 1.0, the base model of Stability AI, or the major model of Stability AI for generating images using a diffusion latent model. And also, if you go up here, you have use this model. It will open up here diffuses. You can see now we have here diffuses, and you can feel free to use that model in your own environment Colab, and it will work for you. And if you go to GitHub, it will direct you to the materials for our course. If you go to the diffuses, here we have the GitHub file, or the notebook file stored on GitHub, that what we will explain in this course about the diffuses library of Hugging Face, where we are generating some faces and also generating images using a prompt with diffusion models using a Stability AI model. And if you open in Colab, it will direct you to the diffuses notebook that we will explain in this course using this notebook. You can see now it's loading. Image processing using Python, where we load an image. You can see we have showed here red channel, green channel, blue channel, and also here we have the diffuses library to generate some faces. And also we have used some prompts to generate and produce some images using Stability AI Stable Diffusion. Now, if we also go down here, we have the datasets library. The datasets library is Hugging Face's data backbone designed to make dataset loading, processing, and benchmarking scalable, reproducible, and framework independent. It abstracts away data source complexity while remaining efficient enough for large-scale training. The main ideas here: load local files, use the same code for small experiments, no change required in downstream pipelines when data source change. And also we have here Apache Arrow backend, zero copy reads, efficient memory usage, fast scaling, filtering and batching, language agnostic data representation. And also dataset transforms and mapping. You can see datasets can be transformed using functional reproducible operations: map, filter, shuffle, select. These are different operations to apply on the dataset and to manipulate the dataset for data ordering and slicing. All transformations are tracked, ensuring consistency between training, validation, and evaluation workflows. And then we have some integration with PyTorch TensorFlow JAX. You can see we have data loader, direct compatibility with PyTorch, which is nice. The data loader class, seamless conversion to TensorFlow. If you are working with TensorFlow, you know that TF-data is the pipeline to work with data in TensorFlow. So this framework agnostic design ensures datasets remain reusable across diverse training stacks and across different libraries. And also we have here Gradio or Gradio interactive ML interfaces. Gradio is an interface framework designed to eliminate the gap between machine learning models and usable user interfaces. Its core goal is to make any ML model testable, shareable, and interactive within minutes without requiring front-end development expertise. Gradio philosophy: ML turned into UI user interface in minutes. Gradio is built around rapid iteration and human-in-the-loop interaction. Researchers and engineers can expose model behavior immediately, enabling fast validation, feedback, and collaboration. No front-end or JavaScript knowledge required. Immediate interaction with live mode outputs, designed for experimentation and rapid prototyping. Core components: we have text boxes, images, audio, chatbots. These components abstract away UI complexity while remaining expressive and flexible. Blocks API. The Blocks API also enables more advanced layout-driven interface design, and later we will see how to use this blocks class by going with gr.blocks as demo. It composes complex user interfaces for modular components. Second, control layout grouping, so how to group some elements, and conditional visibility. Build multi-step and multimodal applications. Blocks allow production-grade interfaces while preserving Gradio's simplicity. And also we have some event system. Gradio uses an event-driven execution model, tightly coupled to model inference. User actions trigger, for example, submit, change, click. So when you change the value, do the following code, or when you click on a button, do the following or execute the following function. Python functions are bound directly to events, supports synchronous and asynchronous execution. State management: maintain conversation history, track intermediate variables, enable multi-step interactive workflows. And here you can see authentication and deployment. Gradio includes built-in deployment features like local hosting for development, public sharing links. You can share the links publicly, authentication for private demos, seamless deployment via Hugging Face spaces. And also here we have research demos versus production tools. Gradio excels in research demonstrations. So if you are publishing a machine learning research paper and you want to create a demo that demonstrates how your model works, you can create that easily. Model validation and comparison, to compare between different models, educational tools and tutorials. While suitable for lightweight production use, Gradio is primarily optimized for experimentation, prototyping, and human-in-the-loop interaction rather than large-scale consumer applications. And here, if you go to click on Hugging Face, it will direct you to the Gradio main website. Build machine learning apps in Python, create web interfaces for ML models in minutes, deploy anywhere, share with anyone. And here we have plenty of explanations on how to use Gradio. And also if you go here, we have Open in Colab. It will direct you to the Colab environment that will contain the code of Gradio that we will explain together in the course. So we have here plenty of cells that explains the functionality and how to use Gradio from the start until you become a professional in Gradio. Now let's go to Hugging Face spaces. Hugging Face spaces act as the deployment and application layer of the Hugging Face ecosystem. They transform trained models into runnable, shareable, and scalable applications, bridging the gap between research prototypes and real-world AI products. Space templates. We have Gradio templates, Streamlit templates, and Docker spaces. Gradio ideal for ML demos. Streamlit suited for dashboards and analytics. Docker full control over runtime and dependencies. Hardware scaling. We have, as we said, CPU, GPU, zero GPU. GPU is high performance generation and real-time interaction. Zero GPU, shared on-demand GPU resources for cost efficiency. And here we can see persistent storage, model checkpoints and fine-tuned weights, cached datasets and intermediate artifacts, user-generated content and application state. And also here we have a very important thing, CI versus /CD. Spaces follow a Git-based CI/CD workflow. Every commit triggers an automatic rebuild. Continuous deployment without manual intervention. Version history enables easy rollback. This provides a simple yet powerful deployment pipeline for ML applications. Spaces as prototypes, minimum variable products, proof of concept demos for stakeholders, user testing environments before full production rollout. And here, if you click on Hugging Face, it will direct you to the spaces page. You can see here we have we have a plethora of spaces here. You can see we have mountains of spaces, and you can try them one by one. Inference and deployment stack. The Hugging Face inference and deployment stack provides multiple layers for serving machine learning models, ranging from simple serverless APIs to high performance enterprise grade inference systems. This flexibility allows teams to balance ease of use, scalability, cost, and latency. Inference API. The Hugging Face Inference API offers a managed serverless way to run models without maintaining infrastructure. So you have the ability to convert whatever model you have, to convert it into an API interface using the Hugging Face Inference API. Instant inference via HTTPS supports NLP, vision, audio, and multimodal, automatic model loading, ideal for prototyping and low to medium traffic applications. Text generation inference, TGI. Text generation inference, TGI, is Hugging Face's high-performance inference engine designed specifically for large language models, optimized for decoder-only LLMs, supports batching, streaming, and KV caching, designed for high throughput and low latency, production ready for large-scale deployments. Endpoints versus local inference. Hugging Face supports multiple deployment strategies depending on operational needs. Inference endpoints, local inference. Inference endpoints, managed scalable cloud-hosted deployments with SLAs. Local inference, self-hosted models running on local or on-prem hardware. Quantization, INT8, GPTQ, IWQ. Quantization reduces model size and computational cost by lowering numerical precision. So we have several ways to reduce or compress the model size. One of them is quantization, and quantization is the process of lowering numerical precision from, for example, float 32 into floating point number 16. INT8, general purpose quantization with minimal accuracy loss. GPTQ, post-training quantization optimized for LLMs. AWQ, activation-aware quantization for improved performance. These techniques enable large models to run efficiently on limited or commodity hardware. Accelerated inference, ONNX, and TensorRT. ONNX is really important. It's called Open Neural Network Exchange. Hugging Face integrates with acceleration frameworks to improve inference performance. ONNX, cross-framework optimization and portability. TensorRT, NVIDIA optimized runtime for maximum GPU performance. Cost versus latency trade-offs. Inference decisions require balancing several competing factors. model size versus response time, numerical precision versus accuracy, managed services versus self-hosting costs, batch size versus real-time responsiveness. So keep in mind, these are trade-offs. When you increase one of them, the other will be decreased. So when you have a large model size, then the response time will be slower. But when you have a smaller model size, the response time will be faster and quicker. Numerical precision versus accuracy. The more the precisions there are in your number, the more the accurate your model is. And the less the precision, the less the model accuracy is. Managed services versus self-hosting costs. So when you host by yourself, then you have some costs, whereas when you have managed services. Batch size versus real-time responsiveness. Hugging Face provides multiple layers of the stack so teams can optimize for their specific costs, latency, or reliability constraints. Training, fine-tuning, and optimization. Hugging Face provides a comprehensive training and optimization stack that supports workflow ranging from lightweight fine-tuning to consumer hardware to large-scale distributed training of foundation models. These tools enable practitioners to balance performance, efficiency, and resource constraints. First, we have full fine-tuning. Update all model parameters for maximum task adaptation. Task-specific head tuning. Freeze the backbone architecture and train lightweight task heads. Continual fine-tuning. Incremental updates while mitigating catastrophic forgetting. These approaches allow teams to trade off accuracy, training cost, and time efficiently. And we have here PEFT, parameter efficient fine-tuning. Parameter efficient fine-tuning, PEFT techniques adapt large models by modifying only a small subset of parameters, LoRa, adapters, and prefix tuning. Let's take a look at LoRa. LoRa, low-rank adapters injected into attention layers, adapters, lightweight modules inserted between transformer layers, prefix tuning, learnable prompt, vectors prepended to model inputs. And we have Accelerate library, which is one of the most important libraries in the Hugging Face world. The Accelerate library abstracts away hardware and distributed training complexity. Unified API for CPU, GPU, and multi-GPU setups, simplified mixed precision and distributed execution, minimal code changes required for scale training. Distributed training. Hugging Face supports scalable training across multiple devices and nodes, data parallelism, multi-GPU integration with PyTorch. Mixed precision training. Mixed precision training improves speed and reduced memory usage. So we have mixed precision, so you are improving speed and reducing memory usage because now your numbers are less precision. Combines floating point 16 or BF16 or floating point 32 numerical stability, enables faster training and larger batch sizes, supported natively via Accelerate and Trainer APIs. Checkpointing and resume strategies. Robust checkpointing mechanisms are built into Hugging Face training workflows. So if you aren't familiar with checkpointing, sometimes when you train large models, you won't train these models in one setting. You need to pause the model training and later you can continue. This is called checkpointing. Periodic saving of model states and optimize the parameters. Resume training seamlessly from intermediate checkpoints, version checkpoints for experiment tracking and comparison. Evaluation, benchmarks, and metrics. Hugging Face treats evaluation as a first-class component of the machine learning lifecycle. Its ecosystem provides standardized, reusable, and transparent evaluation tooling that integrates directly with training, inference, and deployment workflows. We have built-in evaluation tools, unified APIs for computing metrics, seamless integration with transformers and datasets, support for batch and streaming evaluation, reusable and shareable evaluation pipelines. We have also community benchmarks, public leaderboards, community maintained benchmarks across NLP, vision, and speech, open comparison of models under standardized conditions. And also, Hugging Face has task-specific metrics. We have some metrics for classification, accuracy, F1 score, precision, recall. We have some metrics for text generation like BLEU, RUG, Meteor, perplexity, question answering like exact match and F1 score, speech like WER, CER, And for vision, we have MAP and IOU. And also we have some model comparison on the hub, consistent metadata on published evaluation results, benchmark, tags, and public leaderboards, version results linked to specific model versions. And also we have reproducibility and reporting, version pinned models and datasets, documented training and evaluation settings, repeatable pipelines and standardized metric definitions, transparent reporting via model cards and dataset cards. And also here we have safety, ethics, and governance. Hugging Face treats safety, ethics, and governance as integral components of the AI lifecycle. Rather than enforcing a single ethical stance, the platform provides infrastructure, documentation, standards, and access controls that enable responsible development, sharing, and deployment of machine learning models. Model cards, ethics sections, explicit documentation of intended use and potential misuse, disclosure of known biases, limitations, and failure modes, description of trained data, assumptions and scope, guidance for responsible deployment and downstream use. Dataset bias and documentation. Since datasets strongly shape model behavior, Hugging Face emphasizes dataset transparency through dataset cards, clear documentation of data sources and collection methodologies, explicit identification of known biases and representational gaps, licensing terms, consent considerations, and usage constraints. And also keep in mind, there are some gated models that you have to get some approval to be able to use them, and responsible access. Hugging Face supports gated repositories to balance openness with risk mitigation. Access may require user acknowledgement, approval, or license acceptance. Usage conditions and legal constraints can be enforced. Sensitive models can be shared without unrestricted distribution. And also we have some alignment considerations like clear definition of intended behavior and scope, mitigation of harmful, misleading, or unsafe outputs, evaluation against misuse scenarios and edge cases. Open versus restricted models. The platform supports a spectrum of openness tailored to a contextual risk. Open models, fully accessible weights, code, and metadata, while also we have some restricted models, limited access due to safety, legal, or ethical concerns. Here you can see we have Hugging Face for research. Also, you can use Hugging Face as a platform for research if you are a researcher or if you are a machine learning researcher. Hugging Face has emerged as one of the most important infrastructures for modern AI research. It enables reproducibility, open collaboration, and large-scale dissemination of research artifacts, transforming how machine learning research is published, validated, and extended. Reproducing papers. Hugging Face is the primary platform for reproducible AI research. Researchers publish trained model weights alongside code and configurations. Exact model and dataset states can be pinned using commits and revisions. Standardized APIs reduce implementation ambiguity across frameworks. Research repositories, experimental models and baselines, official implementations released by research labs, community replications, benchmarks, and application studies. And also we have open weights movement. Hugging Face is a central driver of the open weights movement in AI, public access to model parameters and configurations. So we have public access to model weights and model parameters, transparent comparison between open and closed models, accelerated collective progress through shared security. Collaboration workflows, shared repositories and organizations for teams and labs. They provide version control for models, datasets, and experiments, issue tracking, discussing, and community-driven improvements. Citations and academic usage. Citation metadata embedded directly in model and dataset cards, extensively referenced in top-tier conferences and journals, increasingly used as the default distribution layer for research artifacts. Here we have Hugging Face for industry and startups. Hugging Face plays a critical role in translating AI research into production-ready systems. Its ecosystem supports startups and enterprises across the full lifecycle, from experimentation to secure, scalable deployment while maintaining flexibility and cost efficiency. production pipelines. We have model discovery, fine-tuning, and version management. So you can discover models, you can fine-tune them, and you can also manage the versions. Integration with CI, CD, and MLOps, machine learning operations, workflows, smooth transition from research experiments to deployed systems. Private hubs. Also, we have some private models, some private datasets and spaces, controlled access within teams and departments, secure sharing of proprietary and sensitive assets. Enterprise security. Token-based authentication. Some models need some token-based authentication for APIs and services. Role-based access control. If you are admin or if you are non-admin, there are some role-based access, control access organizations, compliance-ready deployment options for regulated environments. Model monitoring, versioned model deployments, performance and quality tracking over time, controlled updates, rollbacks, and release management. So production systems require continuous visibility into model behavior. Cost optimization. Methods like quantization and optimized inference engines, flexible hardware selection and auto-scaling options, trade-offs between managed endpoints and self-hosted inference. Hugging Face enables cost-aware deployment strategies. And there are some real-world case studies: NLP-driven search, recommendation, and customer support systems, computer vision applications in healthcare and manufacturing, speech and multimodal AI products in consumer and enterprise settings. And here we have Hugging Face for education. You can use also Hugging Face as a platform for educating yourself. Hugging Face plays a central role in modern AI education by providing open, hands-on, and scalable learning resources. Its ecosystem enables learners, educators, and institutions to move from foundational concepts to advanced real-world AI systems using the same tools employed in research industry. Hugging Face supports structured learning paths that guide learners progressively through the AI landscape. Step-by-step progression across NLP, vision, speech, and generative AI, hands-on interaction with real models and datasets, clear linkage between theory, code, and deployment. Courses and tutorials. We have structured tutorials for transformers, diffusers, and datasets. Code-first explanations using notebooks and runnable examples. Content tailored for beginners, practitioners, and advanced researchers. Community notebooks. Also, there are reproducible experiments and research demos you can benefit from. Fine-tuning, inference, and evaluation examples. Step-by-step educational walkthroughs for models and datasets. Teaching with spaces. Live demonstrations of models and algorithms. Student-accessible applications without local setup. Visual experiential learning that complements theory. And here we have also open curricula, freely accessible educational materials, community reviewed and continuously improved content, adaptable resources for universities and professional training programs. Here also we have Hugging Face plus AI agents. Hugging Face plays a foundational role in modern AI agent systems by providing open, composable, and production-ready models that act as the cognitive and perceptual core of autonomous and semi-autonomous agents. And here we have also so many points about the agents. For example, large language models for planning, reasoning, and multi-step decision-making, fine-tuned task-specific models for specialized skills, open-weight models enabling transparency, inspection, and control. Also here you can see function calling via structured prompts and output schemas, models trained specifically for tool invocation and API interaction, reliable parsing of model outputs for downstream execution. Also we have RAG, retrieval augmented generation pipelines with Hugging Face, embedding models for semantic retrieval, vector database integration through open standards, generative models grounded in retrieved external knowledge. Multimodal agents. We have vision language models, audio text models, multimodal fusion enabling environment-aware agents. Here also we have some frameworks to deploy agents, LangChain for tool orchestration, memory, and planning, compatibility with other agent frameworks and planners, standard APIs, enabling plug-and-play interoperability. Here also we have some Hugging Face ecosystem libraries. Beyond model hosting and inference, Hugging Face provides a rich set of supporting libraries that together form a complete modular machine learning ecosystem. These libraries handle pre-processing, training, evaluation, optimization, alignment, and secure model distribution. For example, Tokenizes, Accelerate, we have the Evaluate library, Optimum, PEFT, PFT, TRLF, RLHF, Safe Tensors library, and also here we have ecosystem summary. Together, these libraries form the invisible infrastructure, the hidden infrastructure of Hugging Face, enabling speed, scalability, safety, and reproducibility across the entire AI lifecycle, from pre-processing and training to deployment and alignment. And here we have Hugging Face and research papers. Here we have some papers. For example, what papers on Hugging Face means. On Hugging Face, a research paper is represented through a dedicated paper page that aggregates everything required to understand, reproduce, and extend the work. A paper page typically links the original research paper, usually on arXiv, associated models hosted on GitHub or on the hub, datasets used or released with the paper, interactive demos and spaces showcasing results and the model, community activities such as likes, downloads, and discussions. Ways papers appear on Hugging Face. We have all the published papers, also have institution or industry releases. We have community-driven references and replications. There are also trending papers and discovery. You can also discover models via some criteria. Hugging Face maintains a dedicated papers section that highlights trending papers based on community engagement, newly released or rapidly adopted research, papers connected to fast-growing model repositories. Relationship with papers with code. Hosting with the runnable artifacts themselves, models, datasets, demos, enabling one-line loading of research models, making reproducibility a default, not a afterthought. Paper cards and metadata. Paper pages on Hugging Face include structured metadata that makes research actionable. Title, authors, and publication source, abstract and concise summaries, linked models and datasets, citations and biptext entries, community signals such as likes and activity. And this website, which is called here the Hugging Face Paper Hub, previously was called Papers with Code. So if you search into here, Papers with Code, it will direct you to the trending papers section on Hugging Face. Here we have a page on Hugging Face dedicated not to models, but specifically or particularly dedicated to papers. Here we have also daily papers. You can see there are daily papers. You can also sort by weekly papers. And also you can sort by monthly papers. And here we have a search bar. You can search any paper with AI. For example, the paper Attention is All You Need. Here you have the paper Attention is All You Need. You can go to it. Here they provide you the authors. They provide you with the title, as you mentioned, some description or the abstract of the paper. You can see the dominant sequence transaction models. And also here we have a link to arXiv page, view arXiv page. You can be directed to arXiv, to the Attention is All You Need paper by Ashish Vaswani et al. And here we have also a view PDF. It will show you a PDF file of the paper directly. And also we can go down and add to collection. Also here you can see the community. They are posting some comments on this paper. Also you can post some comment here and submit your comment, and your comment will show up over here. Okay, so this is the Papers with Code currently hosted on Hugging Face. Here if you go to community, we have blog articles, social posts, and we have here daily papers. So you can access that via the homepage of Hugging Face. Go to the community tab, then open the drop-down menu, go to the daily papers, and it will direct you to this page that contains these papers. And you can see by AK and the research community. Now let's go ahead to our atlas and complete here. So you can see we have so many of the Hugging Face stuff here about the papers, but let's go to recommended academic work on Hugging Face. This section curates foundational and influential academic papers that directly underpin the Hugging Face ecosystem. These works define the theoretical, architectural, and methodological foundations of the libraries, model families, and workflows supported on the Hugging Face platform. Here we have Transformers Library, for example, Attention is All You Need. We have also BERT, Roberta, Decoder Only, for example, GPT model by Alec Radford et al. And also we have the GPT-2 model, encoder decoder models, model families, for example, vision transformers, multimodal models, speech models, code models, audio models, diffuses library that contains foundation models, diffusion models, for example, denoising, diffusion, probabilistic models, DDPM, and DDIM, denoising, diffusion, implicit models. So we have here probabilistic models and implicit models. And also we have score-based and STE frameworks, score-based generative modeling through stochastic differential equation by Yang Song and Stefano Ermon. And also we have here latent diffusion / stable diffusion, which is a latent diffusion model. You can see high resolution image synthesis with latent diffusion models by Rombach and et al. And also we have conditioning and ControlNet, Dreambooth, and LoRa. And here we are. Now we have finished discussing the Hugging Face theory. You can see this is a comprehensive journey and a comprehensive atlas that combines all that you need to have to know about Hugging Face in one page. It's poloclub.github.io Transformer Explainer. So here you can see, first of all, we have some slides that explain the architecture of the transformer. We can close them now, but let's focus on the interface. First, we have an input that will generate. You can see here, data visualization empowers users to visualize. Here you can write whatever sentence you need or whatever sentence you would like, and then you can click generate and it will generate. So let's click generate. You can see now it do one forward pass and then it tries to generate, and now the model generated that. Let's click another time. You can see it will generate another time to visualize the world. So data visualization empowers users to visualize the world, and then click generate around them. First, here you can see we have some embeddings. So we first start by inputting some sentence, inputting a sequence. As we said in here, we first start by inputs. These inputs will be processed by two steps. If you click on the embedding here, you can see we have two steps. We have token embeddings, which are here. We have these IDs. You can see 6,601. So these words, these tokens are mapped into integer IDs. Then these integer IDs are poor representations. They don't convey the semantic meaning. We need another way to represent them. So the best way to represent the words is via the token embeddings and turn them into embeddings, into vector, dense vector embeddings. After that, we preserve the position encoding. Here you can see we have this input embedding layer, which will turn the token IDs, integers, into vectors, high, rich representation vectors. Then we preserve the contextual meaning via this layer, positional encoding layer. Here, this position encoding layer will preserve the meaning. You can see data is at the first position, visualization is at the second position, 1, M is 2, powers 3, uses is 4, 2 is 5, and so forth. So we have token embedding, and then you can see here tokenization splits input text into tokens. Tokenization segments input text into tokens, small units like words or subwords or parts of the words. GPT-2 Small has 50,257 token vocabulary, each with a unique ID. In the token embedding step, every token is matched to a 768 number vector. So each token is converted into a vector of size 768 number inside the vector from a large lookup table. And these vectors are land. These are land vector representations. The model will, when we train the model later, the model will adjust and fine-tune these values inside each vector to best represent the words. And then similar words will be clustered together. The similar words will be clustered far away. These vectors are learned during training to best represent each token's meaning. After this, we have this position encoding layer, which we can see here. Word order matters in language. So the word order or the order of the words matters. Position encoding gives each token information about its place in the sequence. So since Transformer as a standalone architecture doesn't learn the order, doesn't capture the contextual meaning, we need to preserve them. GPT-2 does this by adding a learned positional embedding to the token's embedding. But newer models may use other methods like rope, which encodes position by rotating certain vectors, all aim to help the model understand order in text. After this, after we have processed the text, we can input this processed text into the encoder, which contains the multi-head attention layer. Here we have the you can see we have now the transform block, which is this area that is bordered. If you close this, we have the transformer block, which is the bordered area. We have multi-head self-attention alongside with the multi-layer perceptron. And if you go down here, we have after the embedding, so here we have embedding and we have tokenization, we have token embedding. Here we have the transformer block. The transformer block consists of two things. We have the multi-head self-attention, and then we have after this, we have the multi-layer perceptron. Here, multi-layer perceptron MLP. So these are the two main components. As you can see in the image, we have multi-head self-attention alongside with the feed-forward network. The first thing here, let's start by the first thing, multi-head self-attention. Multi-head means we apply several numerous attention processes in parallel. So here, if you click on them, self-attention lets the model decide which parts of the input are most relevant, are most significant to each token. This helps it capture meaning and relationships, even between far apart words. In multi-head form, the model runs several attention processes in parallel. So in multi-head form, the model runs several attention processes in parallel, each focusing on different patterns in the text. And here you can see inside the multi-head self-attention, we have three key matrices, three important matrices. We have the key matrix, query matrix, and value. The key here, if you click on this, we have query, key, and value. So the key and Q and value are three learned vectors that the attention will learn and update them. To perform self-attention, each token's embedding is transformed into three new embeddings. So each token's embedding, the data, visualization, each word will be converted or transformed into three new embeddings: query, key, and value. You can imagine this as an analogy. We have the search engine Google. When you type in the text, that you type into the search bar, this is the query. So here we have this search bar. You can search in here, what is machine learning? This is the query. This is what you are looking for, what you are searching for. What do you want? What you are looking for behind the scenes. This is the query, the Q. When you click enter, Google suggests multiple websites: IBM blog, Wikipedia blog, Datacamp blog. These are the case. These are the case that suggest themselves, that say, choose me. I have the answer. I am fit to you. I am appropriate to you. Then we try to multiply, here you can see, we try to multiply the K by Q and see how much or how far or how close these two together. Then when we decide that this is the closest K to Q, we choose or we assign them the highest weight to its corresponding value. The value is the actual content, the actual information inside the K. So K will provide us with this V. This is the V, the actual content that will be used or will be passed. So here we have, you can see these parameters, weight and biases. So this transformation is done by applying different weights and biases to each token embedding. These parameters, weights and biases, are optimized through training. Once created, queries compare with keys to measure relevance, to measure similarity, and the relevance is used to weight the values. So if it represents a higher measure, a higher similarity rate, a higher closeness rate, then we assign a high weight to the value. If it's a low relationship or a low correlation between K and V, between Q and K, we assign a low weight to the V. You can see here, them is assigned a high probability, whereas us is assigned a low probability. So you can see here, the V is passed through here, and then we have data moves through the residual connection. Then we have them as 98.32% as a high weight. So we say that the Q is multiplied by the K, and then we scale it via, if you click on here, it will multiply the K by the Q, then it scales that via this equation, Q multiplied by the K transpose divided by the square root of the dimensions of K, then we plus the mask. So here we have the dot product, the multiplication, we multiply Q by K transposed, and we transpose the K because in the multiplication of algebra, we need to transpose the other matrix in order to be compatible to multiply the two matrices or the two vectors. Then we mask it to prevent access to future tokens, and then we have the softmax. We apply the softmax on this masked attention. Then we have a probabilities here. You can see we have some high probabilities. For example, the word visualization is assigned a higher probability. You can see 84, whereas some words here have low probability. For example, 0.03. Then we have this value. We will take these values and then will be passed as the output here. Then we'll go through the multi-layer perceptron. So the main idea of the attention here is that it's a mechanism in machine learning that directs deep learning models what to focus on, what to prioritize. So which parts here should we prioritize? Should the model prioritize and gives the most attention and pay attention to? After this, we have the multi-layer perceptron. The multi-layer perceptron is a feed-forward network that refines the land representations by the attention. Here we have, you can see MLP. So the attention output goes through an MLP, multi-layer perceptron, to refine token representations. A linear layer, which is a feed-forward layer, a simple feed-forward layer, changes embedding values and size using learned weights and bias. Here in the MLP, also we have learned weights, learned biases. So the embeddings here are learned, the KQV are learned, the MLP weights and biases are learned. So you have here three main areas that those areas are learned. A linear layer changes embedding values and size using learned weights and bias. Then a nonlinear activation decides how much each value passes. Many activation types here in the MLP exist. GPT-2 uses GELU, which lets small values pass partially and large values pass fully, helping capture both subtle and strong, robust patterns. After this multi-layer perceptron, here you can see we have this residual connection. And also here we have a residual connection. You can see we have this residual. We pass the raw input as it is without any transformation as the output of this attention or multi-heads of attention. So we combine the transformed data that goes through this attention layer. We combine it with the raw unchanged input from here. We pass it as a residual. You can see residual connection. What is the main idea of residual? Residual connections helps to stabilize the training and the gradient flow of the neural network. So transformers have extra features that enhance the model performance, but aren't core to understanding the basics. For example, a residual connection adds a layer's input to its outputs, keeping information and learning signals from fading, keeping them to not fade, to not vanish through many layers. In GPT-2, it's used twice per block to train deeper stacks effectively. And the same idea, we apply another residual connection in the multi-layer perceptron. So we take the inputs of the multi-layer perceptron and then we pass them here to combine them, to add them with the outputs of the multi-layer perceptron. So here you can see we have residual connection. And also here you can see the layer normalization. So if we return to the image, here we have the inputs to the multi-head attention. We add a residual connection and combine the untransformed version with the transformed version, and then we have the normalization layer. The main idea behind the layer normalization helps stabilize both training and inference by adjusting input numbers so their mean and variance stay consistent. This makes the model less sensitive to its starting weights. This makes the model less sensitive to its initialized weights and helps it learn more effectively. In GPT-2, it's applied before self-attention. before the multi-perceptron and once more before the final output. Then here you can see we have 11 more identical transformer blocks. So we have the same block as this, but multiplied by the nx11. So we can slide between them. You can see we have another block, a third block, and each block tries to learn different representations, different patterns, different weights, and trying to capture the semantic and syntactic representations of each sentence. So here, this block here, you can see, is multiplied nx times. Nx times. They multiplied this block, you can see here, the transformer block, they multiplied this 12 times. So we have 12 of these blocks that will learn the representations in parallel, fully parallelizable manner. After this, so we have here 11 more identical transformer blocks, and then we have the probabilities. You can see here we have the probabilities, and then probability of them, the word them here, token being sampled. We have some sampling techniques here to choose the best next word. You can see we have the scaled logit. So here, temperature hyperparameter. Temperature is the most important hyperparameter in the transformer architecture. It works by scaling the logits before turning them into probabilities. A low temperature, for example 0.2, makes large logits even larger and smaller ones even smaller, favoring the high scoring tokens and leading to more predictable choices. A high temperature, for example 1 or above, flattens the differences, making less likely tokens more competitive and leading to more creative outputs. So if we decrease the temperature, you can see the model is the most deterministic approach. So it takes a strong deterministic approach. So here you can see the word them takes 100%. Whereas if we increase the temperature, the model becomes creative and creative and creative. So the more temperature, the more creative the model. The more creative the model. You can see here the probabilities get distributed over the tokens. And here you can see again we have the top K filtering. We choose the K equals 5. Then you can see the sampling strategy. Finally, we need a strategy, an approach to pick the next token. Many exist, but here are common ones. Greedy search picks. You can see here we have the greedy search. You can change the K. So we can choose the first K, just only the first K. We can choose just 2 Ks or 3 Ks. Here you have K equals 3. We choose the 3 highest performing Ks. And if we increase them, it increases. So here, the top K keeps only the K most likely tokens. And top P keeps the smallest set whose total probability is at least P, trimming unlikely ones early. Then softmax turns the remaining logits into probabilities, and one token is picked at random from the allowed set. So here we can choose whether it was top K or top P. If we choose top P, then it is there. Then it generates the word there. Whereas if we choose the top K, then the top K here is the word, you can see the top K, K equals 1, it chooses the word them. So you can play around with that in your own free time. And then we can slide between the transformer blocks. We can go to the third block, fourth block, and see the attention weights here change. You can see here, the attention weights here are different from here. Every block learns different patterns, learns different representations. Until we have here some examples. For example, IEE, this conference highlights then it tries to generate, highlights the importance, generate of generate. So it moves through all these steps, multi-perceptron, residual probabilities of then it generates. Also you can write your own text. For example, I like reading, generate. Then it tries to generate here. You can see the Q, K, V vectors. I like reading about, generate. You can see here, I like reading about the, generate another time. Now we have the V here combined. I like reading about the history, which is a really nice topic. Then if you go down here, you can read more. What is a transformer? Transformer is a neural network architecture that has fundamentally changed the approach to artificial intelligence. Transformer was first introduced in the seminal paper Attention is All You Need in 2017. So you can feel free to read this paper. Attention is All You Need. paper. And then we have and has since then become the go-to architecture for deep learning models, powering text generative models like OpenAI's GPT, Meta's Llama, and Google's Gemini. Beyond text, Transformer is also applied in audio generation, image recognition, computer vision, protein structure prediction, AlphaFold, and even game playing, demonstrating its versatility across numerous domains. And here we can see we have the Transformer architecture. We have embedding layer. The input text is divided into smaller units called tokens, which can be words or subwords. After this, we have the Transformer block. The block consists of two important mechanisms: the attention mechanism and multi-perceptron. So inside each Transformer block, we have two important core things: attention mechanism and multi-perceptron, and hence the name attention is all you need. We remove recurrence, we remove convolution, we just attend to the most important significant parts and pass them to a multi-perceptron that refines the gradients. Then we have outer probabilities, the final linear layer, and softmax says transform the processed embeddings into probabilities. And you can read the rest in your own time. So you are more than welcome to explore the rest of these. And here you can see we have the main idea behind residual connection. Residual connections were first introduced in the ResNet model in 2015. This architectural innovation revolutionized deep learning by enabling the training of very deep neural networks. Essentially, residual connections are shortcuts that bypass one or more layers, adding the input of a layer to its output. This helps mitigate the vanishing gradient problem, making it easier to train deep networks with multiple transformer blocks stacked on top of each other. In GPT-2, residual connections are used twice within each transformer block, once before the MLP and once after, ensuring that gradients flow more easily and early layers receive sufficient updates during backpropagation.